Most people grow up believing that the speed of light is simply another record waiting to be broken. Airplanes replaced horses, rockets escaped Earth's gravity, spacecraft crossed the solar system with enough time, better engines, and greater determination. It seems reasonable to assume that one day humanity will build a machine capable of travelling as fast as light itself. Modern physics tells a quieter, and far more intriguing, story. The speed of light is not merely the velocity of something that shines across the darkness. It appears to be woven into the architecture of reality itself. Every beam of sunlight reaching Earth, every signal exchange between distant spacecraft, every glimpse of a galaxy whose light began its journey before humanity existed, all carry the signature of the same universal limit. No matter where we look, or how carefully we measure, light always arrives with the same remarkable constancy. This leads to a curious paradox. If nothing in nature has ever been observed carrying information faster than light, why does the universe insist on such a limit? Is it simply a practical barrier? Like the height of a mountain that demands greater effort with every step? Or does crossing that threshold require something fundamentally impossible? Not because of our technology, but because of the way space and time themselves are constructed. The deeper scientists investigated. The stranger the picture became, near light speed. Clocks no longer seem to agree with one another. Distances quietly change. Cause and effect begin to depend on the observer's motion. Even the meaning of time becomes less absolute than everyday experience suggests. None of these discoveries emerge from fantasy or speculation. They arose from careful experiments, precise measurements, and more than a century of scientific investigation. Again and again, nature has answered with extraordinary consistency, even when the answers challenged our deepest intuitions. Yet one question remains waiting beyond them all. If the universe allows us to approach the speed of light, but never quite reach it, what is it protecting? And what would happen if a human being somehow tried to cross that invisible boundary? The universe, as it first appears to us, feels reassuringly familiar. The sun rises each morning, planets trace steady paths around their star, and the stars themselves drift so slowly across the sky that an entire human lifetime notices almost no change. Motion seems straightforward. A cyclist moves faster than a pedestrian. A jet overtakes a car. A spacecraft leaves Earth behind. Every increase in speed appears to follow the same simple pattern. Push harder, burn more fuel, and move faster. For most of human history, this picture seemed complete. The ancient philosophers looked toward the heavens and imagined a cosmos built upon harmony and order. Centuries later, the scientific revolution replaced philosophical speculation with careful measurement. Among its greatest architects was Isaac Newton, whose laws of motion described an astonishing range of natural phenomena with remarkable accuracy. Apples fell toward the Earth for the same reason that the Moon remained in orbit. The same mathematical rules governed cannonballs, oceans, planets, and comets. Within this framework, speed appeared wonderfully uncomplicated. If one ship sailed east at 20 kilometers per hour, while another sailed west at 20 kilometers per hour, each captain would judge the other to be moving at 40 kilometers per hour. Motion depended entirely on the observer. There was no preferred state of rest, only relative movement between objects. This idea became so deeply woven into science that it seemed almost beyond question. Suppose a passenger walks down the aisle of a smoothly moving train to another passenger sitting inside the carriage. The walker may be moving at only a few kilometers per hour, but someone standing beside the tracks measures the person's walking speed plus the speed of the train itself. The two observations differ, yet both are correct because motion is always measured relative to something else. This simple rule works beautifully in everyday life. It explains why rain appears to fall at different angles depending on whether you're standing still or riding in a moving car. It explains why an aircraft must compensate for winds while navigating across continents. It even explains the graceful choreography of planets orbiting the sun while the solar system itself circles the center of the Milky Way. Everything seems to fit. As telescopes improved during the 17th and 18th centuries, Astronomers found that Newton's laws predicted the motions of planets with extraordinary precision. Edmund Halley correctly forecast the return of the comet that now bears his name. The discovery of Neptune came not from direct observation, but because tiny irregularities in Uranus's orbit suggested another unseen planet was exerting its gravitational pull. Mathematics pointed toward a world no one had yet seen, and the telescope later confirmed it. The success was breathtaking. It encouraged scientists to believe that the universe was fundamentally understandable. If enough measurements could be made and enough equations solved, perhaps every future event could, in principle, be predicted. Then attention turned to light itself. At first glance, light hardly seemed mysterious. It illuminated the world, carried warmth from the sun, reflected from mirrors, and bent gently as it passed through glass or water. It behaved as a wave in many experiments, producing beautiful interference patterns much like ripples spreading across the surface of a pond. Yet one simple question resisted an easy answer. Every known wave required something through which to travel. Ocean waves moved through water. Sound travelled through air, liquids or solids. Vibrations spread through strings, metal or stone. If light was also a wave, what exactly was waving? During the 19th century, many physicists proposed an invisible substance filling all of space. They called it the luminiferous ether. This hypothetical medium was thought to permeate the entire universe. Planets would move through it much as ships move through the sea, while light would ripple through it as sound ripples through the atmosphere. The ether seemed to solve an obvious problem. It gave light something to travel through. At first, the idea appeared reasonable. The Earth races around the Sun at nearly 30 kilometers every second. If the ether truly filled space, then our planet should constantly move through it, just as a cyclist feels wind while riding through still air. Earth should experience an ether wind. Light travelling in the direction of Earth's motion ought to behave slightly differently from light travelling across it. The predicted difference was tiny, but by the late 19th century, scientific instruments had become extraordinarily precise. Physicists believed they were on the verge of detecting the invisible ocean through which every ray of starlight supposedly travelled. The experiment seemed almost certain to succeed. Instead, it opened one of the deepest mysteries in the history of science. Again and again, measurements refused to reveal any trace of the ether, no matter how carefully researchers looked. Light behaved as though this invisible medium simply did not exist. The result was deeply unsettling. If there was no ether, then what exactly was carrying light across the vast emptiness between stars? More puzzling still, if motion is always relative, why did every observer seem to measure the same speed for light regardless of how fast they themselves were moving? The familiar universe remained astonishingly successful in describing falling apples, orbiting planets, and moving trains. But hidden within the simple act of switching on a lantern or watching sunlight cross the sky was a contradiction that Newton's magnificent framework could not resolve. The foundations of physics had not collapsed, but for the first time, small cracks had begun to appear, and through those cracks, an entirely different picture of reality was waiting to emerge. The first signs that something was wrong did not arrive with a spectacular explosion of discovery. They appeared quietly, almost reluctantly, hidden inside measurements that refused to behave as expected. Science often advances this way. The most profound revolutions rarely begin with certainty. Instead, they begin when nature continues giving the same unexpected answer, no matter how many times the question is asked. By the late 19th century, physicists believed they possessed an elegant description of almost every known phenomenon. Newton's laws explained motion. James Clerk Maxwell's equations described electricity, magnetism, and light with extraordinary precision. Chemistry was revealing the structure of matter. Thermodynamics explained heat and energy. Many scientists quietly wondered whether only a handful of details remained before physics was essentially complete. It was an understandable belief. Maxwell's equations, published in the 1860s, had achieved something remarkable. They showed that electricity and magnetism were not separate forces but different aspects of a single electromagnetic field. More astonishing still, the equations predicted that disturbances in this field would travel through space at a fixed speed. When physicists calculated that speed using measurements made in laboratories, they obtained a value astonishingly close to the measured speed of light. The conclusion seemed unavoidable. Light itself was an electromagnetic wave. This triumph solved one mystery while creating another. Unlike sound, electromagnetic waves did not appear to require air. Unlike waves on water, they didn't require an ocean. Starlight crossed billions of kilometers of nearly perfect vacuum before reaching Earth, apparently without losing its ability to travel. The ether had been proposed to explain exactly this puzzle, yet every serious attempt to detect it ended in failure. The most famous of these efforts came in 1887 when two American physicists, Albert A. Michelson and Edward W. Morley, built one of the most precise scientific instruments of their time. Their interferometer was a masterpiece of experimental ingenuity. A single beam of light was divided into two identical beams travelling at right angles. After reflecting from carefully positioned mirrors, the beams recombined. If one beam had travelled even slightly faster than the other, because of the Earth's motion through the ether, delicate interference patterns would shift by a measurable amount. The expected effect was extremely small, but the instrument was sensitive enough to detect changes far smaller than the width of a human hair. The experiment was repeated. The apparatus was rotated. Measurements were taken at different times of day. Different seasons were examined as Earth changed its direction while orbiting the Sun. The anticipated shift never appeared. Within the limits of experimental accuracy, light travelled at exactly the same speed in every direction. The result puzzled nearly everyone. It did not merely challenge one hypothesis. It challenged the assumptions beneath classical physics itself. If Earth moved through the ether, why was there no detectable ether wind? If there was no ether, what exactly was oscillating when light travelled? Perhaps the Earth somehow dragged the ether along with it. Perhaps the measuring instruments themselves changed slightly as they moved through space. Perhaps some unknown force was hiding the effect. One explanation after another was proposed. Most were ingenious. None proved fully satisfying. What made the situation particularly uncomfortable was that Maxwell's equations refused to cooperate with Newtonian ideas about motion. Under Newton's mechanics, speed simply added together. Suppose a flashlight was switched on inside a fast-moving spacecraft. Classical intuition suggested that someone outside should measure the speed of the light as the spacecraft's speed plus the speed of the beam itself. That is exactly how thrown baseballs behave. It is exactly how aircraft and ships behave. It is how nearly everything in ordinary life behaves. But Maxwell's equations did not permit such flexibility. They predicted only one speed for electromagnetic waves. There was no extra term, no adjustment, no allowance for the motion of the source. The equations seemed to insist that light always propagated at one fixed speed. For years. This contradiction sat quietly inside physics like a stone beneath calm water. Many scientists believed someone would eventually remove it with a clever correction. Instead, the contradiction grew larger. Astronomers began making increasingly precise observations of stars. One particularly intriguing phenomenon had already been discovered decades earlier by the English astronomer James Bradley. As Earth orbited the Sun, stars appeared to shift their positions slightly over the course of a year. This effect, known as stellar aberration, was not caused by stars actually moving. It arose because Earth itself was moving while the incoming light travelled toward it. The phenomenon resembles walking through gentle rain, even if the rain falls straight downward. A person walking forward tilts an umbrella slightly ahead. The direction of the rain seems altered by the observer's own motion. Stellar aberration demonstrated that Earth's motion certainly influenced how light was observed. Yet it still revealed no evidence for the long-sought ether. Another puzzle emerged from entirely different observations. Mercury, the innermost planet, follows an elliptical orbit around the Sun. Newton's gravity explained almost every aspect of its motion. Almost. The point of Mercury's closest approach to the Sun slowly shifted over time by a tiny amount beyond what Newtonian gravity predicted. Astronomers accounted for gravitational influences from every known planet. Most of the discrepancy disappeared, but not all. A small, unexplained motion remained. It was tiny, barely noticeable, yet persistent. Many hoped another unseen planet closer to the Sun would eventually explain it. No such planet was ever found. Elsewhere, entirely different branches of physics were producing their own uncomfortable surprises. Experiments investigating the behavior of atoms produced results that classical theories struggle to explain. The spectrum of glowing gases displayed sharply defined lines rather than continuous colors. Heated objects emitted radiation in ways existing theories could not reproduce. The stability of atoms themselves seemed mysterious. Individually, each anomaly appeared manageable. Together, they suggested something deeper. The universe was behaving consistently. It was human understanding that was becoming inconsistent. Physicists found themselves in an unusual position. Their equations worked extraordinarily well. Their experiments were extraordinarily precise. Yet the conceptual picture tying everything together had begun to fracture. It was rather like studying an immense cathedral, whose walls appeared perfectly solid from afar. Only upon walking closer did hairline cracks become visible in the stone. No single crack threatened the building, but taken together, they hinted that the foundations beneath it might not be quite what everyone had believed. The mystery surrounding light grew steadily more profound. Its speed appeared immune to the ordinary rules governing motion. Its propagation required no detectable medium. Its behavior remained perfectly consistent across experiments conducted by observers moving in different directions. Nature seemed to be protecting a secret. The question was no longer whether classical intuition contained small errors. The question had become whether space and time themselves had been misunderstood from the beginning. That possibility was almost unthinkable. And yet, at the dawn of the 20th century, one young patent clerk would dare to consider exactly that. His proposal would not simply explain the strange behavior of light. It would redefine the meaning of distance, time, motion, and ultimately, what it means for anything, including a human being, to travel through the universe at all. At the beginning of the 20th century, Albert Einstein was not the celebrated figure whose name would later become almost synonymous with genius. He held no prestigious university chair. He directed no famous laboratory. His daily work took place inside the Swiss Patent Office in Bern, where he examined technical applications for electrical devices and mechanical inventions. From the outside, it seemed an unlikely place for a scientific revolution, yet the routine of the patent office offered something many researchers lacked. It provided long stretches of quiet thought. Einstein spent his days evaluating practical designs, asking whether machines would function exactly as their inventors claimed. That habit of examining assumptions with unusual care would become central to the way he approached physics. He was fascinated by a deceptively simple question. What would the universe look like if someone could travel alongside a beam of light? The question had troubled him since his teenage years. According to Maxwell's equations, light consisted of oscillating electric and magnetic fields moving through space at a fixed speed. If an observer somehow caught up with one of these waves, classical reasoning suggested the wave should appear frozen in place, like an ocean swell suspended forever beneath a motionless ship. But Maxwell's equations allowed no such stationary light wave. They described light only as something that continually propagated forward. A frozen electromagnetic wave simply was not a valid solution. Somewhere, Einstein believed, the contradiction lay not in Maxwell's equations, but in humanity's assumptions about space and time. The challenge was extraordinary. For more than 2 centuries, Newton's picture of the universe had served science remarkably well. Time flowed uniformly for everyone, everywhere. A second on Earth was the same as a second on Mars. A clock carried aboard a moving train should tick at exactly the same rate as one resting quietly in a station. Motion changed positions and velocities, but time itself remained untouched. Few scientists questioned this foundation. Einstein decided to question it. In 1905, often called his Annus Mirabilis, or miraculous year, he published 4 papers that would permanently alter modern physics. One explained the photoelectric effect, helping establish the reality of quantum phenomena. Another offered strong evidence that atoms truly existed by analysing Brownian motion. But it was his paper on special relativity that transformed our understanding of motion. Remarkably, the theory began with only two simple postulates. The first was already familiar. The laws of physics should be the same for every observer moving at constant speed. No experiment performed inside a smoothly moving spacecraft should reveal whether it is drifting through empty space or resting quietly. This principle extended ideas already present in Newtonian mechanics. The second postulate was far more surprising. Every observer, regardless of their own motion, measures the speed of light in a vacuum to be exactly the same. Not approximately the same, not almost the same, exactly the same. This statement seemed impossible. Suppose two spacecraft pass one another in deep space. One remains nearly stationary relative to Earth, while the other travels at an enormous fraction of light speed. Both switch on identical flashlights at the exact moment they cross paths. Common intuition says each crew should disagree about how fast the other beam travels. Instead, special relativity predicts that both observers measure precisely the same speed for both beams. The numbers refuse to add together. Nature protects the speed of light. At first glance, this appears to violate common sense, but Einstein recognized that common sense had been shaped entirely by everyday speeds, where the effects predicted by relativity are far too small to notice. The speed of light is nearly 300,000 kilometers every second. Even the fastest aircraft travel less than 1/10,000th of 1% of that speed. Human experience occupies only a tiny corner of reality. If the speed of light remains fixed, something else must adjust instead. That something else is space and time themselves. The consequences were astonishing. Imagine two lightning bolts striking opposite ends of a long railway platform. An observer standing exactly midway between the strikes sees both flashes arrive simultaneously and naturally concludes that the bolt struck at the same moment. Now consider another observer riding on a fast-moving train passing through the station, because the train moves toward one flash and away from the other. The light from the forward strike reaches the passenger before the light from the rear strike, under Newtonian thinking. This difference would simply reflect the train's motion while the events themselves remained simultaneous. Einstein reached a different conclusion. Since both observers must measure light traveling at the same speed, they cannot both agree about when the lightning actually occurred. Simultaneity itself becomes relative. Events that appear simultaneous to one observer need not be simultaneous to another. This idea was deeply unsettling because it challenged something more fundamental than motion. It challenged the existence of a universal now. Across the vast reaches of the cosmos, there may be no single moment that everyone agrees is happening at once. The universe contains many valid perspectives, each connected by the geometry of space-time. The consequences did not end there. Once simultaneity became relative, time itself could no longer remain universal. Moving clocks would tick differently, not because they malfunctioned, not because of mechanical imperfections, but because time genuinely flows at different rates depending upon motion. This phenomenon, known as time dilation, is one of the most carefully tested predictions in all of modern physics. Atomic clocks flown aboard aircraft accumulate tiny differences compared with identical clocks left on Earth. Satellites orbiting thousands of kilometers above the surface experience both special and general relativistic effects, without correcting for these differences. The global positioning system would accumulate navigation errors of several kilometers each day. Relativity is not merely an elegant theory. It quietly operates inside technologies used by millions of people every hour. Distance also changes. Objects moving near light speed become shorter along the direction of motion, as measured by outside observers. This effect, called length contraction, is not an optical illusion. It is built into the geometry relating different observers' measurements. Neither observer experiences anything unusual locally. Each person's rulers and clocks appear perfectly normal. Only when comparing observations does the remarkable structure of space-time become apparent. Then came perhaps the most famous equation in science. From the framework of special relativity emerged a profound relationship between mass and energy. Energy and mass were not entirely separate concepts. They were different expressions of the same physical reality. Einstein summarized this connection in a concise equation. EMCT, the enormous value of the speed of light squared, means even a tiny amount of mass corresponds to an immense quantity of energy. The stars shine because small fractions of their mass become radiant energy through nuclear fusion. The sun has illuminated Earth for billions of years by slowly converting mass into light. An equation born from understanding motion also explained how stars produce the energy that sustains life. Yet perhaps the most important consequence of special relativity remained almost hidden. As an object gains speed, increasing its energy does not simply make it move proportionally faster. Instead, more and more of the added energy contributes to the relativistic behavior of the object. Its momentum grows dramatically while its speed increases by ever smaller amounts. Approaching light speed becomes increasingly difficult. Each additional increment demands disproportionately more energy than the one before. The mathematics contains no abrupt wall. No physical barrier appears in front of the spacecraft. Instead, the destination quietly recedes. The closer one comes to light speed, the more unreachable it becomes. This realization transformed the question humanity had carried for centuries. The challenge was no longer merely technological. It was woven into the structure of reality itself, if Einstein's theory was correct. Then the greatest obstacle to traveling at light speed was not the weakness of our engines. It was the nature of space-time. But extraordinary ideas require extraordinary evidence. A beautiful theory, no matter how elegant, could never be enough. Only careful observation could reveal whether nature truly behaves this way. Over the next century, experiments on Earth, particles from deep space, and increasingly powerful accelerators would test Einstein's predictions with astonishing precision. And each new result would bring humanity closer to answering a profound question. If the universe itself prevents anything with mass from reaching the speed of light, what exactly happens as we move ever closer to that ultimate limit? Einstein's equations had revealed a universe unlike the one imagined by Newton. Space was no longer a silent stage upon which matter moved. Time was no longer a universal rhythm keeping the same pace for every observer. Together they formed a single fabric, flexible enough that motion itself could change how distance and duration were measured. Yet a theory, however elegant, only becomes part of science when nature agrees. The decades that followed 1905 became one of the greatest periods of experimental confirmation in scientific history. Again and again, observations performed under increasingly demanding conditions returned the same quiet verdict. The universe behaved exactly as special relativity predicted. One of the earliest confirmations came not from distant galaxies or enormous telescopes, but from particles arriving naturally in Earth's atmosphere. Every second, our planet is bombarded by cosmic rays. Most originate far beyond the solar system, accelerated by violent astrophysical events such as exploding stars or the turbulent environment surrounding black holes. When these energetic particles collide with atoms high in the atmosphere, they create showers of new particles that cascade downward toward Earth's surface. Among these are muons. Muons resemble electrons in many ways, but they are about 200 times more massive and remarkably unstable. Left undisturbed, a muon survives for only about 2.2 microseconds before decaying into other particles. That lifetime is astonishingly brief. Even travelling at nearly the speed of light, a muon should cover only a few hundred meters before disappearing. Yet muons are routinely detected at Earth's surface. Many even penetrate deep underground. For years this seemed impossible. They are created roughly 10 to 15 kilometers above the ground. According to classical expectations, almost every muon should decay long before completing the journey. But they do not. Special relativity provides the explanation. From our perspective on Earth, the moving muon's internal clock runs more slowly, although only a tiny fraction of a second passes for us. Far less time passes for the particle itself. Its natural lifetime stretches dramatically when viewed by stationary observers. Curiously, the muon experiences the situation differently. From its own perspective, its lifetime has not changed at all. Instead, the atmosphere has become thinner. The distance between the upper atmosphere and Earth's surface contracts because of its enormous speed. Two entirely different descriptions. One identical outcome. Both agree perfectly because they are connected through the geometry of space-time. This was not merely philosophical elegance, it was measurable. The number of muons reaching Earth's surface matched relativistic predictions with remarkable precision. Nature itself appeared to be keeping Einstein's time. As the 20th century progressed, laboratories began creating particles moving ever closer to light speed. The first particle accelerators were modest machines compared with today's enormous facilities. Yet each new generation pushed charged particles faster than the last. Scientists expected an interesting challenge. Instead, they encountered an invisible wall. Electrons accelerated inside circular machines gained tremendous amounts of energy. Their momentum increased steadily. Their collisions became more violent, but something unexpected happened. Their speeds hardly changed. As particles approached the speed of light, adding more energy produced diminishing returns in velocity. The accelerator continued working. Electric fields continued transferring energy, yet the particles seemed increasingly reluctant to move any faster. The pattern repeated in accelerator after accelerator. Today, facilities such as the Large Hadron Collider accelerate protons to more than 97% of the speed of light. Those numbers are almost impossible to picture. A proton circulating inside the collider travels around its 27-kilometer ring more than 11,000 times every second. Its kinetic energy is thousands of times greater than its energy at rest. Yet despite these enormous increases in energy, its speed differs from the speed of light by only a tiny fraction of a percent. Adding still more energy does not suddenly allow it to cross the boundary. Instead, each improvement becomes progressively smaller. The cosmic speed limit never yields. This behavior is sometimes misunderstood. Popular explanations often say that an object's mass increases as it moves faster. Historically, physicists sometimes describe this idea using the term relativistic mass. Today, however, most physicists prefer a different language. The object's rest mass remains constant. What changes dramatically are its energy and momentum. This modern description avoids confusion while preserving exactly the same measurable predictions. The distinction matters because mass itself is an intrinsic property of the particle. Motion changes how difficult the particle is to accelerate, not what the particle fundamentally is. This subtle shift in language reflects decades of deeper understanding. The equations never changed. Our interpretation became clearer. The consequences extend far beyond particle physics. Astronomers observe nature's own particle accelerators scattered throughout the cosmos. Supernova remnants launch particles across interstellar space. Rapidly spinning neutron stars produce intense electromagnetic fields, capable of accelerating charged particles to extraordinary energies. Near supermassive black holes, enormous jets of plasma stretch across thousands of light years. Within these environments, particles routinely achieve energies vastly exceeding anything humanity can produce. Yet even there, among the most violent places known, the same rule holds. No particle with mass has ever been observed exceeding the speed of light in a vacuum. Nature appears astonishingly consistent. Whether inside a laboratory, beneath the countryside of Europe, or near a black hole millions of times more massive than the Sun, the same limit governs motion. That consistency is one of the strongest reasons physicists trust relativity so deeply. Its predictions are not confined to one experiment. They emerge wherever extreme speeds occur. Another remarkable confirmation arrived from space itself. Beginning in the second half of the 20th century, humanity launched satellites carrying atomic clocks of extraordinary precision. These clocks lose or gain less than a billionth of a second over many days. Such accuracy transformed relativity from an abstract theory into an engineering necessity. Satellites orbit Earth at nearly 4 kilometers every second. According to special relativity, their motion causes onboard clocks to tick slightly more slowly than identical clocks on Earth's surface. At the same time, general relativity predicts that weaker gravity at orbital altitude causes those clocks to tick slightly faster. The two effects partially cancel each other. Engineers calculate both with remarkable precision. Without applying these relativistic corrections every day, GPS receivers would quickly become unreliable. A smartphone guiding someone through an unfamiliar city depends upon equations first written more than a century ago. The technology feels ordinary. The physics behind it remains extraordinary. By now, evidence supporting special relativity came from every direction, from unstable particles born in the upper atmosphere, from giant accelerators probing the smallest constituents of matter, from astronomical observations spanning the galaxy, from satellites quietly orbiting above our heads. Each experiment strengthened confidence that Einstein had uncovered something fundamental about reality itself. Yet another mystery quietly emerged. The closer scientists examined motion near light speed, the more they realized that surviving such a journey involved far more than simply reaching an extraordinary velocity. Even if an impossibly powerful engine existed, even if limitless energy could somehow be supplied, even if the laws of relativity permitted approaching arbitrarily close to light speed, a human traveler would still face dangers unlike anything experienced anywhere on Earth. The empty space between the stars is not truly empty. It contains scattered atoms, microscopic grains of dust, magnetic fields, and a constant rain of high-energy particles. At everyday speeds, these are almost harmless. Near light speed, they become something entirely different. The very emptiness of interstellar space begins to transform into an invisible storm, and that storm raises an unsettling possibility. Long before a human spacecraft ever confronted the ultimate limit imposed by relativity, the universe itself might already have become too hostile for anyone aboard to survive. The question has quietly changed. At the beginning of this journey, the mystery seemed almost philosophical. Why can nothing with mass reach the speed of light now, after following the evidence through relativity, particle physics, and astronomical observation? Another realization begins to emerge. Perhaps reaching light speed is not the first problem. Perhaps surviving the attempt is. This distinction is important because physics separates two very different ideas. One concerns whether the laws of nature permit a particular speed. The other concerns whether a biological organism, built from fragile cells and delicate chemistry, could remain alive while approaching that speed. The answers are not necessarily the same. Relativity tells us that a human spacecraft could, in principle, travel at 90% of the speed of light, or 99%. Even 99.999%. The equations do not suddenly forbid these velocities. They simply demand extraordinary amounts of energy. The closer the spacecraft comes to light speed, the more energy each additional increase requires. But suppose, for a moment, that this obstacle has somehow been overcome. Suppose an unimaginably advanced civilization has solved the engineering challenge. It possesses engines capable of accelerating a spacecraft for months or even years, gradually approaching the greatest speed nature allows. Would the crew survive? Modern physics offers an answer that is both fascinating and deeply unsettling. The first danger comes from something we rarely think about: empty space. When viewed from Earth, interstellar space appears almost perfectly vacant. Between the stars, the average density is astonishingly low. In many regions of the Milky Way, there may be only about one atom in each cubic centimetre, compared with Earth's atmosphere, which contains roughly 10 quintillion billion molecules in the same volume. Interstellar space is an almost unimaginable vacuum. It sounds wonderfully safe. Nothing to collide with, nothing to slow a spacecraft down, nothing but silence stretching across the darkness. Yet velocity changes everything. Walking through a gentle mist barely wets your clothes. Riding a motorcycle through the same mist at highway speed feels entirely different. The droplets strike with much greater force, not because the water has changed, but because your motion has. Relativity amplifies this principle to extraordinary extremes. At 10% of the speed of light, a single hydrogen atom striking a spacecraft carries far more energy than anyone encounters in everyday life. At 99.9% of light speed, the situation becomes almost unimaginable. From the spacecraft's perspective, the sparse gas between the stars is no longer a quiet background. It becomes a relentless beam of incoming particles. Every hydrogen atom ahead behaves like a tiny projectile carrying enormous kinetic energy. The atoms themselves remain tiny. Their impact energy does not. Calculations suggest that individual particles can deliver energies comparable to those produced inside particle accelerators. The spacecraft is effectively flying into a continuous stream of microscopic radiation. Unlike ordinary radiation from the sun, this barrage is generated by the ship's own motion. The faster the journey, the more violent the bombardment becomes. Then there is dust. Interstellar dust grains are astonishingly small. Many measure only fractions of a micrometer across, floating gently between stars. They pose little danger to ordinary spacecraft travelling at tens of kilometers per second. Near light speed, they become something else entirely. Energy depends not only on mass, but on velocity. Even an object weighing only a tiny fraction of a gram can release tremendous energy if moving fast enough. A microscopic dust grain impacting a spacecraft at relativistic speed could produce an explosion far larger than intuition suggests. Engineers studying concepts for future interstellar missions take this possibility very seriously. Shielding against such impacts represents one of the greatest unsolved engineering challenges for any hypothetical relativistic spacecraft. Some proposals envision thick protective layers placed at the front of the vehicle. Others suggest clouds of particles projected ahead to intercept incoming dust before it reaches the main hull. Still others explore magnetic or plasma shielding capable of deflecting charged particles. Each idea offers advantages. Each also faces formidable limitations. Dust is only part of the problem. Space is permeated by energetic particles originating from exploding stars, pulsars, active galaxies, and countless other astrophysical sources. These cosmic rays already reach Earth in enormous numbers. Fortunately, our planet possesses two remarkable defenses. The first is Earth's magnetic field, which deflects many charged particles before they approach the surface. The second is the atmosphere. As cosmic rays collide with atmospheric molecules, they create cascades of secondary particles. Most never reach the ground. Earth quietly protects life every moment. Remove those protections, and the environment changes dramatically. Astronauts aboard the International Space Station receive significantly higher radiation doses than people living on Earth's surface. Future astronauts traveling to Mars will encounter still greater exposure because they spend months outside Earth's magnetic shield. A journey toward light speed magnifies the challenge again. Radiation arriving from the direction of travel becomes concentrated through a relativistic effect known as aberration. Light particles and other incoming radiation appear increasingly compressed toward the front of the spacecraft. The sky itself begins to change. Instead of surrounding the travelers uniformly, much of the visible universe appears squeezed into a brilliant region directly ahead. Stars behind the spacecraft seem to spread apart. Those ahead crowd together. This is not an optical illusion. It is a geometric consequence of moving at relativistic speed. The radiation carried by that concentrated starlight also changes. Another relativistic effect, called the Doppler shift, steadily increases the frequency of light arriving from the direction of travel. Visible light gradually shifts toward ultraviolet. Ultraviolet becomes X-rays. X-rays move toward gamma rays. Ordinary starlight transforms into increasingly energetic radiation. The familiar stars have not changed. The traveler has. This prediction emerges directly from Einstein's equations and is well supported by laboratory measurements of relativistic Doppler effects. Whether future spacecraft will ever experience it firsthand remains unknown, but the mathematics leaves little room for doubt. The forward-facing side of a relativistic spacecraft becomes the most dangerous place on board. Shielding capable of stopping intense gamma radiation is extraordinarily heavy. Shielding capable of surviving repeated impacts from relativistic dust must also withstand enormous mechanical stresses. The very materials used to build the spacecraft become part of the challenge. No known substance offers perfect protection without introducing new engineering problems. Then there is heat. Every absorbed particle deposits energy. Every absorbed photon contributes additional heating. The faster the spacecraft travels, the greater the energy arriving from the front. Eventually, cooling systems must dispose of enormous amounts of waste heat. Unlike on Earth, there is no surrounding air to carry heat away. Spacecraft rely almost entirely on thermal radiation. Large radiators emit infrared energy into space, but radiators themselves have limits. They can release only so much heat before becoming impractically large. This introduces yet another engineering barrier that grows more severe as speed increases. None of these dangers arise because relativity is punishing ambitious explorers. They emerge naturally from the same physical laws that govern every particle and every beam of light in the universe. Nature is not placing warning signs along the road. Nature is simply behaving consistently. Perhaps the most remarkable aspect of all this is that none of these obstacles depend upon human biology. Replace the astronauts with sophisticated robots. Replace living tissue with advanced electronics. Many of the same problems remain. Radiation damages computer systems. Particle impacts erode materials. Extreme heating threatens machinery as surely as it threatens life. The challenge belongs not only to biology, but to matter itself. Yet despite these formidable obstacles, scientists have never concluded that interstellar travel is impossible. Traveling at significant fractions of light speed remains consistent with known physics. The question is whether the engineering demands become so overwhelming that no practical civilization could ever achieve them. That debate continues today, and it leads to an even deeper mystery. If the universe becomes progressively more hostile as speed increases, is this merely a consequence of practical engineering, or is it another clue that the speed of light is woven into reality more profoundly than even Einstein himself could fully explain? Every great scientific mystery eventually reaches the same turning point. Ideas, however elegant, must surrender to observation. By the time Einstein's theory had been debated for several decades, the discussion was no longer centered on philosophy. Physicists were no longer asking whether relativity sounded reasonable. They were asking whether nature itself continued to agree with it under the most demanding conditions that could be created or observed. Again and again it did. What makes the evidence especially compelling is not that it comes from a single remarkable experiment. It comes from many completely different kinds of observations that were never designed to support one another. Each stands on its own. Together, they form one of the strongest bodies of evidence in modern science. One of the clearest examples comes from the world's most powerful particle accelerators. Machines such as the Large Hadron Collider near Geneva do not accelerate spacecraft or planets. They accelerate individual particles, primarily protons, to energies never found naturally on Earth. The engineering required is extraordinary. Thousands of superconducting magnets guide the particles around a circular tunnel nearly 27 kilometers in circumference. Powerful radio frequency cavities add energy each time the particles complete another lap. The process repeats millions of times. With every circuit, the protons become more energetic. Yet something remarkable happens. Even after receiving enormous amounts of additional energy, their speed barely changes. Instead of rapidly approaching and then exceeding light speed, the increase in velocity becomes smaller and smaller. A proton traveling at 90% of the speed of light still has room to accelerate noticeably. A proton already traveling at 99.99999% of light speed can receive vastly more energy, while gaining only an almost immeasurable increase in speed. The energy goes somewhere. It is carefully measured. It simply does not allow the particle to cross nature's apparent limit. The measurements agree with Einstein's equations to astonishing precision. If the equations were even slightly wrong, particle accelerators would reveal the discrepancy almost immediately. Instead, accelerator physics depends upon relativity every single day. Without it, the machine simply would not function as designed. Evidence also arrives from much farther away. Throughout the Milky Way and beyond, violent astrophysical events accelerate particles to energies far beyond anything humans can currently produce. When massive stars explode as supernovae, enormous shock waves sweep through surrounding space, accelerating charged particles to extraordinary speeds. Rapidly rotating neutron stars generate magnetic fields trillions of times stronger than Earth's, launching particles outward in brilliant beams. Near supermassive black holes, gigantic jets extend thousands, sometimes millions, of light years into intergalactic space. These environments serve as nature's own particle laboratories. If any place in the universe were capable of breaking the light speed barrier, these would seem the most likely candidates. Yet despite decades of observation, astronomers have never detected a massive particle exceeding the speed of light in a vacuum. Some particles come astonishingly close. None cross the threshold. This absence is itself an observation. Science often learns not only from what nature reveals, but from what it consistently refuses to reveal. Another line of evidence comes from particles called neutrinos. Neutrinos are among the most elusive known particles. Trillions pass through your body every second without leaving the slightest sensation. Because they interact only very weakly with matter, they can travel enormous distances through planets, stars, and entire galaxies almost completely undisturbed. For many years, physicists wondered whether neutrinos might possess unusual properties that could challenge relativity. In 2011, one experiment briefly suggested that neutrinos might have arrived slightly earlier than light would have over the same distance. The announcement attracted worldwide attention. If confirmed, it would have required physicists to rethink some of the foundations of modern theory. But science does not settle extraordinary questions through excitement. It settles them through verification. Independent investigations soon identified the cause. A faulty fiber optic connection and a timing calibration problem had introduced a small measurement error. Once corrected, the apparent faster-than-light result disappeared. Subsequent experiments confirmed that neutrinos obey relativistic predictions. The episode became an important reminder of how science works. Unexpected results are not ignored. They are tested relentlessly. Only those that survive repeated scrutiny become accepted. Relativity survived once again. Evidence also comes from something surprisingly familiar. Light emitted by fast-moving astronomical objects does not simply become brighter or dimmer. Its wavelength changes. When a galaxy moves away from Earth, its light shifts toward longer wavelengths, becoming redder. When an object approaches, the light shifts toward shorter wavelengths. This Doppler effect is familiar in everyday life through sound. The pitch of a passing ambulance siren changes because successive sound waves are compressed ahead of the vehicle and stretched behind it. Light behaves similarly. At relativistic speeds, however, the relationship is governed not by classical physics but by Einstein's equations. Astronomers measure these shifts constantly. Binary stars orbit one another. Gas circles black holes. Jets emerge from active galaxies. Every observation reinforces the same mathematical framework. No alternative theory has explained such a broad range of measurements with comparable success. Then there are unstable particles created inside accelerators. Many exist for only tiny fractions of a second before decaying. Scientists can predict their lifetimes extremely accurately. As these particles travel faster and faster, their observed lifetimes increase exactly as special relativity predicts. This phenomenon is measured repeatedly across many different particle species. The agreement is so consistent that it has become an ordinary part of experimental particle physics. No laboratory treats time dilation as an exotic possibility. It is simply another measurable property of nature. Astronomers encounter relativity on even larger scales. When binary neutron stars spiral toward one another, they gradually lose orbital energy by emitting gravitational waves. General relativity predicted this decades before such waves were directly detected. The observed orbital decay matched theoretical predictions with extraordinary precision. Later, observatories such as LIGO and Virgo directly measured gravitational waves themselves, providing another powerful confirmation of Einstein's broader picture of space-time. Although these observations concern gravity rather than special relativity alone, they reinforce the underlying idea that space-time behaves according to principles very different from everyday intuition. The evidence stretches across an astonishing range of scales: subatomic particles, human-built accelerators, Earth-orbiting satellites, exploding stars, orbiting neutron stars, supermassive black holes, expanding galaxies. Each occupies a completely different physical environment. Each involves different instruments, different scientists, different methods, different sources of uncertainty. Yet all converge upon the same conclusion. Light occupies a unique place within the laws of nature. Perhaps even more striking is what scientists have failed to observe. No experiment has ever demonstrated reliable transmission of information faster than light through empty space. Claims occasionally appear. Careful investigation consistently finds conventional explanations, measurement errors, misunderstood observations, or effects that never actually transfer usable information. This distinction matters greatly. Physics allows certain mathematical quantities, wave patterns, or apparent motions to exceed the speed of light under specific circumstances. For example, the point where a laser beam sweeps across the moon can appear to move faster than light because no physical object travels along that path. Similarly, the expansion of the universe allows sufficiently distant galaxies to recede from one another faster than light due to the expansion of space itself, not because they are moving through space in the ordinary sense. These situations do not violate relativity. They simply illustrate that speed can mean different things in different physical contexts. When it comes to matter, energy and information travelling locally through space-time, every observation remains consistent with the same fundamental limit. By now, the evidence has become difficult to dismiss. Relativity is not trusted because Einstein was brilliant. It is trusted because the universe continues confirming it every time we ask sufficiently careful questions. Yet the evidence leaves one profound mystery unresolved. Experiments reveal that the speed limit exists. They show that matter obeys it. They demonstrate that countless physical processes depend upon it. But observation alone cannot fully answer a deeper question. Why should the universe possess such a limit at all? Why this speed? Why not faster or slower? The measurements tell us what nature does. They do not necessarily tell us why reality is built this way. To explore that question, scientists must move beyond direct observation and begin comparing the deepest ideas modern physics has to offer. Once the evidence becomes overwhelming, science enters a different phase. The question is no longer whether a phenomenon exists. The question becomes how best to understand it. By the middle of the 20th century, few physicists doubted that the speed of light represented a fundamental limit for matter and information travelling through space-time. Countless experiments had confirmed the predictions of relativity with extraordinary precision. From particle accelerators to atomic clocks, from cosmic rays to distant galaxies, the observations all pointed in the same direction. Agreement about the measurements, however, did not eliminate every deeper question. Why should nature possess such a limit in the first place? Physics can describe remarkable accuracy without always explaining ultimate origins. Newton described gravity long before anyone understood what gravity truly was. Maxwell described electromagnetic waves before the quantum nature of light was known. Likewise, Einstein's relativity describes the consequences of the cosmic speed limit with extraordinary success, while leaving room for discussion about why reality has precisely this structure. Over the past century, several complementary ways of thinking about this question have emerged. Importantly, these are not all competing in the sense that only one can be correct. Some are different interpretations of the same established mathematics. Others attempt to extend physics beyond its current boundaries. Understanding the distinction is essential. The accepted scientific fact is straightforward. Every local experiment performed so far indicates that light travels through a vacuum at approximately 299,792 km per second, and no object with non-zero rest mass has been observed accelerating beyond that speed. That statement rests on observation. The explanation begins with accepted theory, within special relativity. The speed of light is not viewed as an arbitrary restriction imposed upon moving objects. Instead, it arises naturally from the geometry of space-time itself. This perspective is perhaps the most widely accepted among physicists. To appreciate it, it helps to stop thinking about space and time as separate things. Every event in the universe occupies both a location and a moment. Einstein united these into a single four-dimensional structure called space-time. Objects do not merely move through space. They trace paths through space-time. Light occupies a very special kind of path. Every flash of light, whether emitted by a candle or a distant quasar, follows what physicists call a null trajectory along these paths. The structure of space-time itself fixes the speed at which light propagates. From this viewpoint, asking why light travels at that speed is somewhat like asking why the angles inside a flat triangle add to 180 degrees. It is not an additional rule. It is part of the geometry. Massive objects follow different kinds of paths. No amount of continuous acceleration can transform one kind of path into another. The mathematics simply does not allow it. Within this framework, the speed of light is less a barrier than a boundary separating fundamentally different categories of motion. This interpretation explains many observed phenomena elegantly: time dilation, length contraction, relativistic momentum, the relativity of simultaneity, all emerge naturally from the geometry rather than requiring separate physical mechanisms. For many physicists, this simplicity is deeply persuasive. Yet another equally accepted perspective focuses not on geometry alone, but on fields. Modern particle physics describes nature in terms of quantum fields filling all of space-time. Electrons are excitations of the electron field. Quarks arise from quark fields. Photons are excitations of the electromagnetic field. In this picture, empty space is not truly empty. It contains the underlying fields from which particles emerge. The speed of light reflects fundamental properties of the electromagnetic field itself. More specifically, Maxwell's equations show that electromagnetic waves propagate according to measurable characteristics of free space, represented by two constants, the vacuum permittivity and the vacuum permeability. Long before Einstein published special relativity, these constants already implied one specific propagation speed. Relativity later revealed that this speed was far more fundamental than anyone had realized. Today, quantum electrodynamics, one of the most successful theories ever developed, builds upon both Maxwell's theory and quantum mechanics. Its predictions have been tested to astonishing precision, often agreeing with experiments to more than 10 decimal places. Within this framework, light speed is not viewed as an arbitrary number. It is built into the properties of the quantum fields describing electromagnetism. Again, however, this answers how rather than why. Why should those fields possess precisely those properties? Physics continues to describe. The ultimate origin remains deeper. Some physicists approach the question from yet another direction. General relativity extends Einstein's ideas beyond constant motion to include gravity. Instead of treating gravity as an invisible force pulling objects together, general relativity describes massive bodies as curving space-time itself. Planets orbit the Sun not because they are continuously pulled sideways, but because they follow the straightest possible paths through curved space-time. Within this description, light always travels locally at the same speed. Gravity does not slow light in the ordinary sense. Instead, gravity changes the geometry through which light travels. This distinction explains remarkable observations. During a solar eclipse in 1919, astronomers measured starlight bending around the Sun exactly as general relativity predicted. Today, entire galaxies act as gravitational lenses, bending light from even more distant galaxies behind them. The light continues moving locally at its usual speed. The path itself is curved. Once again, the cosmic speed limit survives. Then there are ideas that remain scientifically motivated but are not yet established. One active area of research involves quantum gravity. General relativity describes space-time on enormous scales with extraordinary success. Quantum mechanics describes the microscopic world equally well. Yet combining the two into one complete theory remains among the greatest unsolved problems in physics. Several candidate approaches exist. String theory proposes that the fundamental building blocks of nature are not point-like particles, but tiny vibrating strings. Loop quantum gravity suggests that space-time itself may possess an underlying discrete structure at unimaginably small scales. Other approaches explore causal sets, asymptotic safety, emergent space-time, and additional mathematical frameworks. Each seeks to explain reality more deeply than current theories can. Crucially, none has yet received decisive experimental confirmation. Scientists continue investigating because existing theories become incomplete under extreme conditions such as the centers of black holes or the earliest moments after the Big Bang. Could the speed of light emerge from an even deeper microscopic structure of space-time? Possibly. At present, no one knows. That uncertainty must be stated clearly. Another speculative question occasionally appears in both scientific literature and popular discussion. Could the speed of light itself have been different in the early universe? Some theoretical models have explored what are known as varying speed of light cosmologies. These ideas attempt to address certain puzzles in cosmology by allowing the effective speed of light to differ under extremely early conditions. Such models remain highly speculative. They are not part of established scientific consensus. Current observations continue to support a constant local speed of light throughout all tested environments. Likewise, proposals involving wormholes, warp drives, or exotic space-time geometries sometimes give the impression that relativity has been bypassed. The reality is more subtle. Certain mathematical solutions to Einstein's equations permit unusual space-time geometries. Theoretical concepts such as the Alcubierre warp drive describe a bubble of expanding and contracting space-time that could, in principle, move effectively faster than light relative to distant observers. However, these ideas require forms of matter with properties not known to exist in usable quantities, including negative energy densities far beyond anything currently achievable. No experimental evidence indicates that practical warp drives are possible. They remain valuable theoretical exercises rather than engineering projects. This distinction illustrates an important habit of modern science. Accepted theory is treated differently from plausible speculation. Plausible speculation is treated differently from unsupported imagination. Healthy scientific curiosity depends upon maintaining these boundaries. After more than a century of investigation, the situation is remarkably clear. Facts. Objects with mass have never been observed exceeding the speed of light locally. Evidence. Experiments across physics repeatedly confirm relativistic predictions. Accepted theory. Special and general relativity explain these observations with extraordinary success. Active hypotheses. Quantum gravity may reveal a deeper explanation for why space-time possesses its observed structure. Speculation. Future theories could reshape our understanding under conditions far beyond current experiments. Unknown. Why reality ultimately possesses precisely this geometry, these fields, and this universal speed remains unanswered. Science has explained an enormous amount, yet one fascinating possibility still remains to be explored. If everything we have learned is correct, what would the universe actually look like from the perspective of someone travelling unimaginably close to the speed of light? The answer is stranger than almost anything science fiction has imagined. Suppose, for a moment, that every practical obstacle we've encountered could somehow be overcome. Suppose an extraordinarily advanced civilization has developed propulsion systems capable of accelerating a spacecraft for years without exhausting its energy supply. Suppose it has devised shielding strong enough to survive collisions with interstellar dust and sophisticated systems capable of protecting its crew from the relentless radiation concentrated ahead of the ship. The spacecraft is still not travelling at the speed of light. According to everything established so far, that remains impossible for an object with mass. Instead, it travels astonishingly close, perhaps 99.999% of the speed of light. This is no longer an engineering question. It is a thought experiment grounded in accepted relativity. By asking what such travellers would actually experience, we begin to see why approaching light speed transforms far more than velocity. It transforms reality as it's perceived. The first surprise concerns time. In everyday life, time feels universal. A minute measured by one clock appears identical to a minute measured by every other clock nearby. Human experience reinforces this intuition so completely that it is difficult to imagine any alternative. Relativity quietly disagrees. As speed increases, the passage of time aboard the spacecraft slows relative to clocks that remain behind. This is not a mechanical fault. The astronauts would notice nothing unusual about their own watches. Their heartbeats remain steady. Conversations proceed normally, meals, sleep, and daily routines all unfold exactly as expected. Inside the spacecraft, life feels entirely ordinary. Only when comparing clocks with distant observers does the difference become apparent. Imagine a journey to a star located 10 light-years from Earth. From Earth's perspective, even a spacecraft travelling extremely close to light speed would require a little more than 10 years to complete the outward trip. Because it can never quite reach light speed itself, more than 2 decades would pass before a return mission arrived home. Families would grow older. Children would become adults. Entire chapters of civilization might unfold. For the crew, however, much less time could pass. Depending on the exact speed, only a few years might elapse aboard the spacecraft. This outcome is not speculative. It follows directly from the experimentally confirmed equations of special relativity. Both descriptions are equally valid. Earth measures one interval. The travellers measure another. Neither observer experiences incorrect time. Time itself depends upon the path taken through space-time. This realization often gives rise to what is popularly called the twin paradox. Imagine identical twins. One remains on Earth. The other departs aboard a relativistic spacecraft, eventually turning around and returning home. Upon reunion, the travelling twin is younger. At first glance, this seems contradictory. Each twin saw the other moving, so why should only one age less? The resolution lies in the fact that the journey is not perfectly symmetrical. The travelling twin changes direction, undergoing acceleration during departure, turnaround, and arrival. The earthbound twin remains approximately within one inertial frame. Relativity predicts a definite outcome. confirmed indirectly through many experiments involving clocks and unstable particles. Time is not an illusion. It simply does not flow identically along every possible path through space-time. The next surprise concerns distance. From Earth, the destination remains 10 light-years away. From the spacecraft, it does not. As speed increases, distances measured along the direction of travel contract. To the crew, the gap separating the stars becomes shorter. This effect is called length contraction. Again, it is not an optical trick. It is part of the geometry relating different observers. One might be tempted to ask which distance is the real one. Relativity answers with an unexpected simplicity. Both are. Distance, like time, depends upon the observer's state of motion. Neither perspective is privileged. Together they describe the same underlying space-time. The universe itself begins to change appearance. Relativistic aberration compresses much of the visible sky into the direction of travel. Stars that once surrounded the spacecraft gradually crowd toward the forward view. Constellations lose their familiar shapes. Regions behind the ship appear to stretch outward, while the sky ahead becomes increasingly concentrated. An astronaut would not recognize the heavens as seen from Earth. The transformation is not merely geometric. Light itself changes color. The relativistic Doppler effect steadily shifts incoming wavelengths. Stars directly ahead become increasingly blue. Visible light moves into the ultraviolet. Ultraviolet shifts toward X-rays. Eventually, even the gentle glow of ordinary stars can be transformed into highly energetic radiation striking the forward shield. Meanwhile, light arriving from behind shifts toward longer wavelengths. Blue stars become white. White stars become red. Some eventually fade into infrared wavelengths invisible to the human eye. The universe grows brighter in one direction and darker in the other. This effect has been measured countless times for light emitted by rapidly moving astronomical objects. The thought experiment merely extends those same equations to an observer travelling at extreme speed. Brightness changes as well. Radiation arriving from the forward direction becomes concentrated. Astronomers call this relativistic beaming. Light that was originally spread across much of the sky becomes focused into a smaller region ahead. Active galaxies with jets aimed nearly toward Earth appear extraordinarily luminous partly because of this effect. A relativistic traveller would experience the reverse. The forward sky would become increasingly intense, the rearward sky increasingly dim, even the cosmic microwave background. The faint afterglow of the Big Bang that currently fills the universe at a temperature of about 2.7 Kelvin would no longer appear uniform. As velocity increased, its microwave photons would be Doppler shifted. Ahead of the spacecraft, their wavelengths would shorten dramatically. Behind the spacecraft, they would lengthen even further. At sufficiently extreme speeds, radiation that is now completely invisible could be shifted toward visible or even higher energy wavelengths. The oldest light in the universe would acquire an entirely new appearance. All of these changes arise without altering the universe itself. The stars have not moved. The galaxies have not changed. Only the observer's motion has transformed the measurements. This is one of relativity's deepest lessons. Reality does not consist solely of isolated objects. It also includes the relationships between observers and events. Yet one question naturally follows. If time slows so dramatically for the travellers, why not simply continue accelerating forever? Wouldn't they eventually cross the entire observable universe within a single human lifetime? The answer is subtle. From the crew's perspective, enormous cosmic distances can indeed become dramatically shorter because of length contraction. Proper time aboard the spacecraft may remain surprisingly modest. However, this does not allow information or matter to outrun light locally. Observers elsewhere still measure the spacecraft moving below light speed. Causality remains intact. The structure of space-time remains unbroken. No paradox appears. The travellers experience less time. The universe outside continues aging normally. This remarkable consequence has inspired countless works of science fiction. Yet it also reveals a profound emotional truth about relativity. A civilization capable of travelling near light speed would not merely visit distant stars. It would travel into the future of the worlds it leaves behind. Friends would grow old. Cultures would evolve. Languages might change beyond recognition. Entire histories could unfold during what feels to the crew like only a handful of years. Relativity offers no path back to the shared present once such a journey begins. The travellers carry their own clocks. The universe carries another. This possibility remains entirely consistent with accepted physics. It does not violate the cosmic speed limit. Instead, it reveals one of its most extraordinary consequences, and when we widen our view beyond a single spacecraft, an even greater realization begins to emerge. The same relativistic principles governing one human voyage also shape exploding stars, orbiting black holes, energetic galaxies, and the evolution of the cosmos itself. The mystery of surviving near light speed is no longer only about travelers. It is about understanding the universe that makes such journeys possible. A spacecraft racing through interstellar space may seem like an isolated story. A handful of travelers, a single vessel, one remarkable journey between distant stars. Yet the deeper we follow relativity, the more we discover that the same principles governing that imagined voyage also govern the larger structures in the universe. The speed of light is not simply a limit placed upon explorers. It is woven into the evolution of stars, galaxies, black holes, and even the history of the cosmos itself. To understand why, it helps to step back from the spacecraft entirely. Consider the Sun every second. Its core converts roughly 600 million tons of hydrogen into helium through nuclear fusion. Not all of that mass remains inside the newly formed helium nuclei. A small fraction is transformed into energy, precisely as described by Einstein's relation between mass and energy. That energy begins an extraordinarily long journey. A photon produced near the Sun's core does not travel directly into space. Instead, it spends thousands to hundreds of thousands of years scattering repeatedly through the dense solar interior before finally escaping from the visible surface. Only then does it begin the familiar 8-minute journey to Earth. Those 8 minutes matter. When we look at the Sun, we never see it as it is at that instant. We see it as it was a little more than 8 minutes ago. If the Sun could somehow vanish instantly, an impossible scenario according to known physics, Earth would continue orbiting normally and continue receiving sunlight for approximately 8 more minutes. Information itself requires time to travel. The speed of light governs not only illumination but causality. The same principle extends across the galaxy. The nearest star beyond the Sun, Proxima Centauri, lies about 424 light-years away. Every telescope on Earth observes that star not as it exists today, but as it existed more than 4 years in the past. The Andromeda Galaxy appears as it was roughly 2.5 million years ago, long before modern humans emerged. The James Webb Space Telescope and other observatories peer even farther into cosmic history, capturing galaxies whose light began its journey more than 13 billion years ago. Astronomy is unlike any other science. Its observations are inherently historical. Looking farther into space also means looking farther back in time. The speed of light makes the universe a vast archive. Every photon carries information from another era. Every distant object is a message sent across unimaginable spans of time. Without the finite speed of light, this remarkable connection between distance and history would disappear. The universe would reveal itself all at once. Instead, it unfolds like layers of an ancient manuscript. The story grows even more fascinating around black holes. According to general relativity, gravity is not a force acting across empty space in the traditional Newtonian sense. It is the curvature of space-time produced by mass and energy. Near extremely compact objects, this curvature becomes profound. Light itself follows the geometry. Around a black hole exists a boundary known as the event horizon. Outside this boundary, light can still escape, although its path may be dramatically bent. Inside it, every possible future-directed path through space-time leads inward. This distinction is subtle. Popular descriptions sometimes say that a black hole's gravity becomes stronger than light. That phrasing is not quite accurate. Light never slows below its local speed. Instead, space-time becomes curved so severely that every available direction points deeper toward the black hole. The geometry itself has changed. This extraordinary prediction has received powerful observational support. Astronomers have watched stars orbit the invisible object at the center of our galaxy, revealing the presence of a supermassive black hole nearly 4 million times the mass of the Sun. The Event Horizon Telescope has even produced images of the shadows cast by black holes in distant galaxies, matching predictions made by general relativity with remarkable accuracy. These observations reinforce a profound idea. The speed of light continues to define the structure of space-time even in the most extreme gravitational environments known. Relativity also shapes some of the universe's most violent explosions. When massive stars exhaust their nuclear fuel, their cores collapse. Some become neutron stars, others form black holes. The collapse releases enormous amounts of energy, launching supernova explosions that briefly outshine entire galaxies. During these events, matter is accelerated to extraordinary velocities. Shock waves race through surrounding gas. Neutrinos stream outward. Intense radiation floods nearby space. Yet throughout the chaos, the familiar limit remains. Nothing carrying information outruns light in the surrounding vacuum. The explosions are spectacular precisely because enormous energies are released while still obeying the same underlying laws. The same principles govern active galaxies. At the centers of many galaxies reside supermassive black holes containing millions or even billions of solar masses. As gas falls inward, gravitational energy is converted into heat and radiation. Some of this material is redirected into narrow jets that extend thousands of light years into intergalactic space. These jets move at speeds astonishingly close to that of light. To observers on Earth, portions of the jets sometimes appear to move faster than light itself. This effect is called apparent superluminal motion. The name sounds dramatic, but the explanation is entirely consistent with relativity. Because the jets travel almost directly toward us, while moving only slightly below light speed, the light emitted at different moments reaches Earth in compressed intervals. The geometry creates the illusion of faster-than-light motion. Careful measurements reveal that no physical object actually exceeds light speed. It is another reminder that appearances can differ from the deeper structure of space-time. Relativity also governs the lives of neutron stars. These incredibly dense remnants pack more mass than the Sun into a sphere only about 20 kilometers across. Many rotate hundreds of times each second. Their magnetic fields accelerate charged particles to enormous energies, producing beams of radio waves, X-rays, and gamma rays. When these beams sweep across Earth, astronomers detect them as pulsars. The timing of many pulses is so stable that they rival atomic clocks. Some are used to test general relativity with extraordinary precision. Again, the same framework describing an imagined interstellar voyage also explains the behavior of some of the most exotic objects in existence. Then there are gravitational waves. For a century after Einstein predicted them, they remained one of the most elusive consequences of general relativity. These ripples in space-time are produced when massive objects accelerate, particularly during the inspiral and merger of neutron stars or black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves from merging black holes. The signal matched Einstein's predictions with astonishing accuracy. Equally remarkable was its speed. Subsequent observations comparing gravitational waves with electromagnetic radiation from the same astrophysical events showed that gravitational waves travel at essentially the speed of light, within extraordinarily tight observational limits. Two entirely different messengers, one shared cosmic speed. The universe appeared even more unified than before, on the largest scales of all. The speed of light defines what astronomers call the observable universe. The universe itself may extend far beyond what we can ever see. Yet because light has travelled for only a finite amount of time since the Big Bang, there exists a horizon beyond which no information has yet reached us. This cosmic horizon is not a physical wall. It is a limit imposed by time and the finite speed at which information propagates. Every telescope, no matter how powerful, remains confined within it. Thus, the speed of light does more than govern motion. It shapes knowledge itself. There are regions of the cosmos whose light simply has not had enough time to arrive. Whether civilizations exist there, whether galaxies form differently, or whether unknown structures lie beyond our horizon remains inaccessible to direct observation, not because the universe hides them intentionally, but because information cannot outrun the geometry of space-time. Seen from this larger perspective, The question that began with a human traveller has become something far broader. The cosmic speed limit influences how stars shine, how galaxies evolve, how black holes bend light, how gravitational waves carry information, and how much of the universe humanity is capable of observing. It is no longer merely a restriction. It is one of the organizing principles of the cosmos. And yet, an even deeper pattern begins to emerge. Relativity, quantum physics, black holes, the early universe, and the very limits of observation all seem to converge on the same unanswered frontier. Perhaps the true mystery is not why humans cannot survive travelling at light speed. Perhaps it is why so many of nature's deepest theories appear to meet precisely at that boundary. As our journey has unfolded, ideas that first seemed unrelated have begun to draw together. A beam of sunlight leaving the surface of a star, an unstable particle racing through Earth's atmosphere, a satellite carrying an atomic clock, a supermassive black hole bending the light of an entire galaxy, a spacecraft attempting to approach the speed of light. At first, these appear to belong to entirely different branches of science: astronomy, particle physics, relativity, engineering, cosmology. Yet modern physics increasingly suggests that they are not separate stories at all. They are different expressions of the same underlying reality. One of the most remarkable examples of this unity comes from the relationship between energy and gravity. When Einstein introduced his famous equation, E mc, many people understandably interpreted it as a statement about nuclear power or the enormous energy hidden inside matter. Those applications are certainly important, but the equation carries a deeper meaning. Mass and energy are not fundamentally different substances. They are different forms of the same physical quantity. This seemingly simple idea quietly links phenomena across the entire universe. The light escaping from the sun carries energy. Because energy contributes to gravity, that light also contributes, however slightly, to the gravitational influence of the sun. Likewise, the intense radiation trapped inside the early universe helped shape how matter eventually gathered into galaxies. Energy affects gravity. Gravity shapes space-time. Space-time governs motion. Motion determines how energy is observed. The circle quietly closes. Another unexpected connection appears inside neutron stars. These extraordinary objects contain matter, compressed far beyond anything achievable in terrestrial laboratories. A single teaspoon of neutron star material would weigh billions of tons on Earth. Under such conditions, neither ordinary atomic physics nor classical gravity is sufficient. Quantum mechanics becomes essential because it governs the behavior of densely packed particles. General relativity becomes equally essential because gravity has become extraordinarily strong. Both theories are required simultaneously. Yet here we encounter one of the greatest unresolved tensions in all of science. Quantum mechanics and general relativity are both astonishingly successful. Independently, each has survived countless experimental tests. Together, however, they resist complete unification. This conflict remains hidden during ordinary human experience, because gravity is usually weak while quantum effects dominate only the microscopic world. Inside neutron stars, near black holes, and during the earliest moments after the Big Bang, those comfortable separations disappear. Nature demands that both theories operate together. Physics has not yet discovered exactly how. This is not merely an abstract mathematical problem. It may determine how space-time itself behaves under the most extreme conditions imaginable. Black holes provide another remarkable meeting point. General relativity predicts their formation naturally. Quantum mechanics introduces an unexpected complication. In the 1970s, Stephen Hawking combined ideas from both fields and found that black holes should not remain perfectly black forever. Instead, quantum effects near the event horizon allow them to emit an extremely faint form of thermal radiation, now known as Hawking radiation. The prediction does not arise because particles escape directly from inside the event horizon. Rather, it emerges from the behavior of quantum fields in curved space-time. This subtle distinction matters enormously. Hawking radiation has not yet been directly observed from astrophysical black holes because it is far too weak compared with other sources of radiation. Nevertheless, the theoretical argument is considered one of the most important bridges ever built between quantum theory and gravity. It also creates a profound puzzle. If black holes slowly evaporate through Hawking radiation, What ultimately happens to the information describing everything that fell into them? Quantum mechanics strongly suggests that information cannot simply disappear. General relativity seems to imply that it can. This apparent contradiction became known as the black hole information paradox. For decades, it has inspired some of the deepest work in theoretical physics. String theory, quantum information theory, the holographic principle, black hole thermodynamics, all have contributed ideas toward resolving the paradox. No universally accepted solution has yet emerged. Once again, the boundary marked by light speed quietly reappears. The event horizon itself is defined by the behavior of light. The information paradox depends upon quantum fields propagating at relativistic speeds. Even one of the greatest unsolved problems in theoretical physics returns us to the same fundamental structure of space-time. Surprising connections also appear when astronomers study the early universe. For hundreds of thousands of years after the Big Bang, the universe remained so hot that light scattered continuously from free electrons. Space was filled with a brilliant plasma through which photons could travel only short distances before colliding again. Eventually, as expansion cooled the cosmos, electrons combined with atomic nuclei to form neutral atoms. Light suddenly traveled much more freely. The photons released during that era continue crossing the universe today. We observe them as the cosmic microwave background. This faint glow represents the oldest light that can currently be seen directly. Its tiny temperature variations preserve a detailed record of conditions in the young universe. Remarkably, measurements made by satellites such as COBE, WMAP, and Planck agree extraordinarily well with the predictions of modern cosmology. The same speed of light governing laboratory experiments also determines how this ancient radiation has crossed more than 13 billion years of cosmic history. Another connection emerges from gravitational lensing. When astronomers observe a distant galaxy whose light passes near another massive galaxy on its way to Earth, gravity bends the light into arcs or multiple images. These beautiful distortions do more than confirm general relativity. They allow astronomers to map matter that cannot be seen directly. Most of that invisible matter is believed to be dark matter. Dark matter neither emits nor absorbs light in the ordinary way. Its existence is inferred through gravity. Without the predictable behavior of light traveling through curved space-time, one of astronomy's most powerful tools for studying dark matter would disappear. Light becomes not only something to observe, it becomes a probe revealing otherwise hidden structures. Even gravitational waves and light have begun working together. In 2017, astronomers observed the merger of two neutron stars through both gravitational waves and electromagnetic radiation. For the first time, two entirely different messengers described the same cosmic event. The gravitational waves revealed the motion of space-time itself. Light revealed the expanding debris, radioactive elements, and energetic aftermath. This approach, known as multi-messenger astronomy, has transformed modern astrophysics. Instead of relying upon one type of signal, scientists now combine many. Photons, gravitational waves, neutrinos, cosmic rays, each carries different information. Together, they create a far richer picture of the universe. This growing unity across physics is striking. Fields once treated as largely independent increasingly overlap. Particle physics informs cosmology. Astronomy informs quantum theory. Black holes illuminate thermodynamics. Information theory contributes to gravity. What once appeared as separate branches now resemble different pathways leading toward the same mountain summit. Yet there remains one place where every path seems to disappear into mist. That place lies at the smallest conceivable scales. According to current understanding, if space-time possesses an underlying microscopic structure, it becomes relevant near what physicists call the Planck scale. This distance is unimaginably tiny, roughly 1.610, 35 meters, far beyond the reach of any existing experiment. At these scales, quantum fluctuations of space-time itself may become unavoidable. The familiar distinction between space and time could break down. The smooth geometry described by general relativity may no longer remain smooth. No one yet knows. Every successful theory eventually reaches a boundary beyond which it can no longer confidently predict reality. For Newton, it was extremely high speeds and strong gravity. For general relativity, it is the quantum structure of space-time. For quantum mechanics, it is gravity under extreme conditions. All roads converge upon the same frontier, and remarkably, every one of them passes through the speed of light, not because light explains everything, but because light marks the framework within which everything we currently understand must operate. That realization carries us naturally into the present day. Humanity has built instruments more sensitive than Einstein could ever have imagined. We have begun detecting gravitational waves, imaging black holes, mapping ancient radiation, and observing galaxies from the dawn of cosmic history. Each new instrument promises answers, yet, almost without exception, each answer reveals an even deeper question waiting just beyond it. For much of human history, the greatest limitation in astronomy was simple. The universe was too far away. Even the brightest stars appeared as little more than points of light. Galaxies were faint smudges. Black holes were entirely invisible. The earliest chapters of cosmic history lay hidden beyond the reach of every telescope. The laws of physics could be written on paper. Testing them against the universe was another matter entirely. Over the past few decades, that situation has changed dramatically. Modern astronomy has entered an era in which entirely new kinds of instruments allow scientists to observe the cosmos in ways that earlier generations could scarcely have imagined. The goal is no longer merely to see farther. It is to measure reality with enough precision to challenge even our most successful theories. One of the clearest examples is the James Webb Space Telescope. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb is optimized for infrared wavelengths. This allows it to detect light that has been stretched by the expansion of the universe over billions of years. Many of the galaxies Webb studies emitted their light when the universe was only a few 100 million years old. These observations do not directly test whether humans can survive traveling near light speed. Instead, they examine the same underlying framework. The light arriving at Webb has travelled immense distances while obeying the same relativistic principles that govern every beam of light produced in laboratories on Earth. Each ancient photon serves as another confirmation that the laws of physics appear remarkably consistent across both space and time. Webb has also begun revealing galaxies that formed surprisingly early in cosmic history. These discoveries have inspired lively scientific discussion. Importantly, they do not overturn relativity. Instead, they encourage researchers to refine models describing how the earliest galaxies assembled after the Big Bang. This illustrates an important feature of modern science. Unexpected observations do not automatically destroy established theories. They often improve them. The strongest theories survive because they continue explaining an enormous range of evidence, even while incorporating new discoveries. Ground-based observatories have become equally extraordinary. Facilities such as the Very Large Telescope in Chile and the Keck Observatory in Hawaii combine enormous mirrors with adaptive optic systems capable of correcting for distortions caused by Earth's atmosphere. The result is an astonishing level of clarity. Astronomers now routinely track stars orbiting the supermassive black hole at the centre of the Milky Way. One star in particular, known as S2, completes an orbit roughly every 16 years. Its motion carries it deep into the intense gravitational field surrounding the black hole. Repeated observations have confirmed predictions of general relativity, including the subtle precession of its orbit. Once again, Einstein's theory continues passing increasingly demanding tests. The Event Horizon Telescope represents another remarkable achievement. Rather than constructing one impossibly large telescope, scientists linked radio observatories across Earth into a global network using a technique called Very Long Baseline Interferometry. Together, these observatories effectively created a virtual telescope nearly the size of our planet. In 2019, the collaboration released the first image of the shadow surrounding the supermassive black hole in the galaxy M87. Later observations revealed similar structures around the black hole at the centre of our own galaxy. These images are not photographs in the ordinary sense. They are carefully reconstructed from enormous quantities of observational data. Yet they provide powerful confirmation that light behaves near black holes almost exactly as general relativity predicts. Perhaps the most revolutionary new observatories are those that do not observe light at all. LIGO in the United States, Virgo in Europe, and Kagura in Japan detect gravitational waves. These instruments measure changes in distance smaller than the diameter of a proton across arms, several kilometers long. Their sensitivity borders on the astonishing. When two black holes merge billions of light-years away, the ripples passing through Earth stretch and compress space-time by incredibly tiny amounts. Laser interferometers record these changes directly. Each detection allows physicists to examine gravity under conditions impossible to reproduce in laboratories. So far, Einstein's equations have continued matching observation with remarkable success. Gravitational wave astronomy is still young. Every new observing run expands the catalogue of detected mergers. Future detectors, including the planned Laser Interferometer Space Antenna, or LISA, will extend this capability into space, allowing scientists to detect lower frequency gravitational waves produced by supermassive black holes and other enormous systems. Another rapidly developing field is precision cosmology. Space missions such as Planck have mapped the cosmic microwave background with extraordinary accuracy. Tiny fluctuations in this ancient radiation encode information about the composition and evolution of the universe shortly after the Big Bang. Combined with galaxy surveys, these observations allow astronomers to estimate quantities such as the age of the universe, its average density, and the proportions of ordinary matter, dark matter, and dark energy. Yet even here, new mysteries have appeared. One example is the so-called Hubble tension. Different methods of measuring the expansion rate of the universe produce slightly different results. Measurements based on the early universe disagree modestly with measurements based on relatively nearby galaxies. The discrepancy is not yet large enough to overturn modern cosmology. It may eventually be explained through improved observations or previously unrecognized systematic effects. Alternatively, it could hint at new physics. Scientists do not yet know. The careful distinction between possibility and conclusion remains essential. Particle physics is also advancing. Although the Large Hadron Collider has not discovered evidence for supersymmetry or many other proposed extensions of the Standard Model, it has continued measuring known particles with increasing precision. Each improvement narrows the space available for alternative theories. Null results matter. Knowing where new physics does not appear is just as important as discovering where it does. Meanwhile, researchers continue searching for dark matter using underground detectors shielded from cosmic rays by kilometers of rock. Experiments such as Xenon, LZ, and others attempt to observe extraordinarily rare interactions between hypothetical dark matter particles and ordinary matter. Thus far, no definitive detection has occurred. The mystery remains open. Elsewhere, enormous neutrino observatories buried deep beneath Antarctic ice or submerged in clear ocean water detect particles arriving from violent cosmic events. The IceCube Neutrino Observatory has identified astrophysical neutrinos carrying energies far beyond those produced in human accelerators. These elusive particles provide a completely new way of studying the high-energy universe. They travel almost undisturbed across billions of light-years, carrying information inaccessible through light alone. Computer simulations have become another essential scientific instrument. Modern supercomputers model galaxy formation, black hole mergers, stellar evolution, and the growth of cosmic structure. These simulations do not replace observation. Instead, they allow researchers to compare theoretical predictions with real measurements. When simulations succeed, confidence in underlying theories increases. When they fail, scientists search for missing physics or overlooked assumptions. Artificial intelligence is beginning to assist this process. Machine learning algorithms now help identify gravitational lenses, classify galaxies, search for exoplanets, and detect subtle patterns hidden within enormous astronomical datasets. Importantly, these systems do not replace scientific reasoning. They accelerate discovery by helping researchers recognize promising signals that might otherwise remain unnoticed. Across all these efforts, a common theme emerges. Modern astronomy is becoming increasingly interdisciplinary. Photons, gravitational waves, neutrinos, cosmic rays, computer simulations, quantum theory, general relativity, each contributes a different piece of the puzzle. Together, they form an increasingly detailed portrait of the universe. Yet despite this extraordinary progress, one fact remains remarkably consistent. No observation has revealed a breakdown of the cosmic speed limit. Instead, every new instrument extends its domain, whether studying black holes, distant galaxies, relativistic jets, or the oldest light in existence, the same underlying principles continue to describe reality with astonishing reliability. Paradoxically, this success creates its own challenge. When a theory explains so much so well, discovering where it finally becomes incomplete becomes extraordinarily difficult. Scientists now find themselves searching not for obvious contradictions, but for tiny deviations hidden within measurements of extraordinary precision. Perhaps the next breakthrough will emerge from an unexpected gravitational wave signal, perhaps from subtle features of the cosmic microwave background, perhaps from dark matter, perhaps from quantum experiments probing spacetime itself. No one yet knows. What is clear is that humanity has never possessed more powerful tools for asking questions about the cosmos, and yet, despite all these remarkable instruments, the deepest mystery of our journey remains unresolved. We understand the cosmic speed limit better than ever before, but understanding its consequences is not the same as understanding its ultimate origin. Beyond the reach of today's telescopes and accelerators, important questions still wait unanswered. There is a quiet misconception that often accompanies scientific progress. As telescopes become more powerful and equations more precise, it is tempting to believe that mystery steadily disappears. Each discovery seems to illuminate another corner of the universe, replacing uncertainty with knowledge, given enough time. It might appear that every question will eventually find its answer. The history of science tells a different story. Every major advance has expanded the boundary of the unknown. The invention of the telescope revealed that the Milky Way contained countless stars, but it also revealed countless galaxies beyond it. The discovery of atoms explained the chemistry of matter, while opening the entirely new world of quantum physics. General relativity transformed gravity from a force into the geometry of space-time. Yet it exposed questions about black holes and the origin of the universe that Newton's theory had never even asked. Knowledge does not eliminate mystery. It often refines it. Our journey toward the speed of light follows the same pattern. After more than a century of experiments, physicists possess extraordinary confidence in special relativity. Its predictions have been confirmed across laboratories, particle accelerators, satellites, and astronomical observations with remarkable precision. Yet confidence in a theory is not the same as complete understanding. Some of the most profound questions remain unanswered. Perhaps the deepest concern, space-time itself. General relativity describes space-time as smooth and continuous. Every location can, in principle, be divided into smaller and smaller intervals without limit. Quantum mechanics encourages a different intuition. Many physical quantities that once seemed continuous are now understood to possess discrete properties. Energy comes in quanta. Angular momentum is quantized. Electric charge appears in fixed units. Does space-time itself possess an underlying microscopic structure? No one knows. Current experiments simply cannot probe distances anywhere near the Planck length, roughly 1.6 × 10^35 meters, to appreciate how small that is. Imagine shrinking a single proton until it became comparable in size to the observable universe. The Planck length would still be unimaginably smaller than the original proton. No existing accelerator can approach such scales. Even the Large Hadron Collider operates enormously far from the energies where quantum gravity is expected to become important. Technology itself imposes a limitation. Another unanswered question concerns the origin of inertia. Relativity tells us how objects respond as they accelerate toward light speed. It describes the relationship between energy, momentum, and motion with extraordinary success. But why should matter possess inertia at all? Why should mass resist acceleration? The Higgs field provides an important part of the answer. Interactions with the Higgs field contribute to the masses of many elementary particles. The discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed this essential component of the Standard Model. Yet the story remains incomplete. Most of the mass inside ordinary matter does not come directly from the Higgs field. For example, the proton is composed of quarks held together by gluons through the strong nuclear force. The overwhelming majority of the proton's mass arises not from the intrinsic masses of its constituent quarks, but from the energy of their interactions. Mass itself emerges from multiple physical processes, Exactly why these processes possess their observed values remains an active area of research. Dark matter presents another enduring mystery. Astronomical observations strongly indicate that visible matter accounts for only a small fraction of the total matter in the universe. Galaxies rotate too rapidly. Galaxy clusters remain too tightly bound. Gravitational lensing reveals more mass than telescopes can directly observe. The evidence for dark matter is substantial. Its identity remains unknown. Is it composed of new particles? Could gravity itself behave differently under certain conditions? Most physicists currently favour particle explanations because they account for a broad range of observations, but definitive experimental confirmation has not yet arrived. The uncertainty remains genuine. Dark energy is, if anything, even more mysterious. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating. Something appears to be driving galaxies apart at an ever-increasing rate. The simplest explanation introduces a cosmological constant into Einstein's equations. This model successfully describes many observations, yet its physical origin remains deeply puzzling. Quantum field theory predicts vacuum energies enormously larger than the value inferred from cosmological observations. Reconciling these two numbers represents one of the greatest unsolved problems in theoretical physics. The universe expands. The measurements are reliable. Why it expands this way remains uncertain. Black holes continue challenging our understanding as well. General relativity predicts singularities, regions where known mathematical descriptions break down. Most physicists suspect that singularities signal the limits of current theory rather than literal physical infinities. A successful theory of quantum gravity may eventually replace them with a deeper description. Until such a theory exists, certainty remains impossible. The information paradox also remains unresolved despite remarkable theoretical progress. Different candidate solutions preserve different aspects of existing theory. Some invoke subtle quantum correlations. Others rely upon holographic principles or new space-time structures. No experimental observation has yet distinguished decisively among them. Perhaps the greatest uncertainty concerns the earliest moments of the universe. The observable universe preserves an extraordinary record extending back to roughly 380,000 years after the Big Bang, when the cosmic microwave background was released. Earlier than that, observations become increasingly indirect. Nuclear synthesis provides evidence from the first few minutes. Particle physics offers insights into even earlier epochs. Beyond that, confidence gradually gives way to inference. What happened during the first tiny fraction of a second? Did cosmic inflation occur exactly as current models describe? Was inflation driven by a quantum field? Could entirely different processes have operated? Observations continue narrowing the possibilities. None has yet produced a definitive answer. Even the question of whether the speed of light has always possessed exactly its present value remains open only in a very limited theoretical sense. Some speculative cosmological models explore varying effective speeds under the extraordinary conditions of the early universe. These ideas remain outside established consensus. Current observations strongly support a constant local speed of light throughout all environments that have been tested. Future measurements may place even tighter limits upon such possibilities. For now, the standard picture remains remarkably successful. Technology also defines the frontier. Many phenomena relevant to fundamental physics occur under conditions humanity cannot directly access. The centers of black holes, the first instance after the Big Bang, the interiors of neutron stars beyond certain densities, energies trillions of times greater than those produced by current accelerators. Science advances by observing natural laboratories whenever possible. Sometimes nature provides them, sometimes it does not. This limitation is not a failure. It is part of the scientific process. The universe is under no obligation to place its deeper secrets within easy reach. Indeed, some questions may remain experimentally inaccessible for generations. Others may require entirely new observational techniques not yet imagined. History suggests caution. Again and again, scientists have underestimated the ingenuity of future technology. No one in Newton's time could have anticipated radio telescopes. No one in Einstein's era could have predicted gravitational wave observatories. Perhaps equally transformative instruments await humanity centuries from now. Or perhaps certain questions truly lie beyond direct experimental reach. We cannot yet distinguish between those possibilities. That uncertainty deserves respect. One lesson has emerged repeatedly throughout this documentary. Science grows strongest not when it claims certainty beyond the evidence, but when it identifies precisely where certainty ends. Everything we know about approaching the speed of light rests upon extraordinarily solid foundations. Everything we do not know begins just beyond them. That boundary is not a place of failure. It is where discovery begins, and standing upon that boundary, physicists now look toward an even more ambitious horizon, not merely asking how the universe behaves, but wondering what entirely new ideas might someday reveal why it behaves this way at all. Every generation inherits a different frontier. For the sailors of the 15th century, it was the horizon beyond the familiar coastline. For 19th century physicists, it was the invisible structure of atoms. For astronomers in the 20th century, it became the distant galaxies that slowly revealed an expanding universe. Today, the frontier lies somewhere even more elusive. It is not hidden behind a mountain or beyond the reach of a ship. It exists where our most successful theories begin to overlap, where their extraordinary accuracy remains undeniable, yet where none of them can fully describe reality on its own. The speed of light stands quietly at the center of that frontier, not because physicists doubt that light travels at its measured speed. That measurement has been confirmed countless times. The mystery lies deeper. Why should space-time possess exactly this structure? Why should causality be organized in precisely this way? Why does the universe appear to distinguish so clearly between objects with mass and particles such as photons that always travel at light speed? These questions remain unanswered. The challenge is not a lack of imagination. Modern theoretical physics contains no shortage of ambitious ideas. The challenge is evidence. Science advances by comparing theory with observation, and the observations required to probe these questions are extraordinarily difficult to obtain. One possible path forward lies in gravitational wave astronomy. The first direct detections have already transformed our understanding of black holes and neutron stars, but they may represent only the beginning. Future observatories promise far greater sensitivity. The planned Laser Interferometer Space Antenna, known as LISA, will place 3 spacecraft millions of kilometers apart in heliocentric orbit, forming a vast triangular detector capable of measuring gravitational waves with much lower frequencies than Earth-based instruments can observe. Those waves are expected to originate from events unlike anything LIGO routinely detects: slow mergers of supermassive black holes, compact binary systems throughout the Milky Way, possibly even subtle signals carrying information from the earliest stages of cosmic history, if such observations reveal unexpected deviations from general relativity. They could provide invaluable clues toward a deeper theory of gravity. They may also confirm Einstein's picture with even greater precision. Either outcome advances science. Another frontier lies in particle physics. The Large Hadron Collider continues exploring energies previously inaccessible to experiment, although no confirmed evidence for new fundamental particles beyond the Standard Model has yet emerged. Researchers continue refining measurements of known particles to extraordinary precision. Sometimes revolutions begin not with spectacular discoveries, but with tiny discrepancies. A minute deviation between prediction and observation can reveal entirely new layers of reality. History offers several examples. The small irregularities in Uranus's orbit led to the discovery of Neptune. The unexplained motion of Mercury helped motivate general relativity. Today, physicists search for similarly subtle clues. Future accelerators, if constructed, may probe energies beyond the reach of current facilities. Whether they uncover new particles, new symmetries, or entirely unexpected phenomena remains unknown. Cosmology provides another promising direction. Upcoming observatories such as the Vera C. Rubin Observatory will map billions of galaxies across enormous volumes of space. Other missions, including the European Space Agency's Euclid spacecraft and NASA's Nancy Grace Roman Space Telescope, will study dark matter, dark energy, and the large-scale structure of the universe with unprecedented detail. Their measurements may help resolve current tensions in cosmology. Alternatively, they may expose limitations in existing models. Again, the distinction matters. Scientists do not build these observatories because they expect current theories to fail. They build them because the most reliable way to test successful theories is to challenge them with even better observations. The search for dark matter also continues. If dark matter consists of new elementary particles, future underground detectors, space-based experiments, or collider observations may eventually identify them directly. Such a discovery would reshape our understanding of galaxies, cosmic evolution, and perhaps even the earliest moments after the Big Bang. Yet there is another possibility. Dark matter might prove more elusive than expected. It may require ideas that do not yet exist. Science must remain open to both outcomes. Perhaps the most ambitious frontier concerns quantum gravity. Every candidate theory seeks to answer a question that has quietly accompanied us throughout this documentary. What is space-time made of? General relativity treats space-time as smooth. Quantum mechanics suggests that nature often possesses underlying discrete structures. Reconciling these views remains one of the greatest intellectual challenges in science. String theory proposes that the apparent particles of nature arise from unimaginably tiny vibrating strings, whose different modes correspond to different particles. The mathematics naturally incorporates gravity, making it an attractive framework for many researchers, yet direct experimental confirmation remains absent. Loop quantum gravity approaches the problem differently. Rather than introducing strings, it explores the possibility that space-time itself possesses an atomic structure. Area and volume may exist in discrete units, much as energy exists in quanta. Again, the mathematics is sophisticated. Again, decisive observational evidence has not yet arrived. Several other approaches continue active development. Causal dynamical triangulations, asymptotic safety, emergent gravity, causal set theory. Each attempts to describe reality more deeply than present theories can. At this stage, none commands universal acceptance. This situation sometimes disappoints those hoping for definitive answers. Yet uncertainty is not a weakness of science. It is evidence that scientists are asking questions at the very edge of what observations currently allow. Perhaps the next breakthrough will come not from a larger telescope or a more powerful accelerator, but from an entirely new way of thinking. History repeatedly reminds us that conceptual revolutions often accompany technological ones. Einstein required no giant laboratory to develop special relativity. His breakthrough came from re-examining assumptions that generations had accepted without question. Future physicists may one day perform a similar transformation. The equations describing the universe could become part of an even deeper framework, one that explains why space-time possesses its observed geometry, rather than simply describing how that geometry behaves. Whether such a theory exists remains unknown. There is also a more philosophical implication. If the speed of light truly represents a fundamental feature of reality, then it defines not merely the limits of travel but the limits of communication, observation, and shared experience throughout the cosmos. No civilization, however advanced, can simply erase those constraints without changing the structure of space-time itself. The universe preserves a kind of causal order. Events influence one another through finite intervals. Stars do not illuminate planets instantaneously. Galaxies cannot exchange information without waiting for light to cross the immense distances between them. Even the observable universe possesses a horizon beyond which information has not yet reached us. The cosmic speed limit is therefore more than a physical constant. It is part of the architecture that allows cause to precede effect. It shapes history on every scale, from the lifetime of unstable particles to the evolution of galaxies, from the ticking of atomic clocks to the expansion of the universe itself. Every successful observation continues pointing toward the same remarkable conclusion. And yet, one final question remains. Even if humanity someday masters fusion propulsion, antimatter engines, or technologies not yet imagined, even if future generations routinely cross the distances between nearby stars, even if spacecraft travel closer to the speed of light than anything ever built before, will they ever truly understand why the universe chose this limit? Or will the speed of light always remain one of those rare boundaries that science can describe with extraordinary precision, while its deepest origin continues to lie just beyond the horizon of human knowledge when our journey began? We started with an assumption that feels almost inevitable. Human history often appears to be the story of overcoming limits. We crossed oceans that once seemed endless. We learned to fly through skies that had belonged only to birds. We walked upon the moon, sent robotic explorers beyond every major planet, and built telescopes capable of looking back across nearly the entire history of the observable universe. Against that background, it seems natural to believe that the speed of light is simply another frontier waiting for a future generation, a difficult destination, an extraordinary engineering challenge, one more mountain to climb. Yet the universe has quietly guided us toward a different understanding. The closer we examined light, the less it resembled an obstacle placed before humanity, and the more it revealed itself as part of the framework from which reality is built. Its speed is not merely the velocity of sunlight crossing empty space. It determines how information travels. It connects cause with effect. It shapes the geometry of space-time. It governs how stars shine, how galaxies are observed, how black holes bend light, and how the history of the universe reaches our telescopes one photon at a time. The deeper we looked, the more often the same boundary appeared. It was present inside the equations of Maxwell before Einstein understood their full meaning. It emerged again through the Michelson-Morley experiment, which quietly revealed that nature was stranger than classical intuition had imagined. It appeared inside particle accelerators, where enormous increases in energy produced ever smaller increases in speed. It revealed itself in unstable particles descending through Earth's atmosphere, their internal clocks slowing exactly as relativity predicts. It became visible in the orbits of stars circling black holes, in gravitational waves crossing billions of light years, and in the faint microwave glow left behind by the early universe. Different experiments, different instruments, different centuries, the same conclusion. That consistency is one of science's greatest achievements, not because it proves that every question has been answered, rather because it demonstrates how observations gathered independently can converge upon a single picture of nature. This picture does not ask us to abandon wonder. It invites a deeper kind of wonder. Throughout history, humanity often imagined knowledge as something that would eventually remove mystery from the world. Modern astronomy suggests almost the opposite. Each answer has expanded the landscape of unanswered questions. When Newton described gravity, he did not know why gravity existed. When Einstein described space-time, he did not fully explain why space-time possesses its remarkable structure. Today, physicists continue searching for a theory capable of uniting gravity with quantum mechanics. While dark matter and dark energy remain among the greatest unsolved mysteries in science, knowledge has grown enormously, so has the horizon beyond it. Perhaps this is not disappointing. Perhaps it is exactly what makes science such an extraordinary human endeavour. Unlike myths, science does not promise final certainty. Unlike dogma, it does not ask that uncertainty be feared. Instead, it treats uncertainty as an invitation. Every unanswered question becomes a direction rather than a barrier. Every unexpected observation becomes an opportunity to understand reality more deeply than before. This attitude has carried humanity remarkably far. A century ago, black holes existed only as mathematical possibilities. Today we have observed their shadows. Gravitational waves were once faint ripples predicted only by equations. Now they are measured directly. Planets around other stars were once matters of speculation. Thousands are now known. Each generation inherits mysteries that seemed impossible to investigate only decades earlier. It is reasonable to believe that future generations will continue this tradition. They may construct observatories far larger than those of today. They may detect the particles composing dark matter. They may discover a successful theory of quantum gravity. They may even build spacecraft capable of travelling at significant fractions of the speed of light, carrying explorers between neighbouring stars. If that day comes, the experience will almost certainly be unlike anything previous civilizations could have imagined. The travellers will watch time unfold differently from those who remain behind. Distances between stars will contract according to the geometry of space-time. The sky itself will transform as starlight shifts toward higher energies ahead of the spacecraft and fades behind it. The voyage will not resemble the familiar journeys of ships crossing oceans. It will be an encounter with the deepest architecture of reality itself. And yet, one feature of that reality is expected to remain unchanged. No matter how advanced the civilization, no matter how sophisticated the propulsion system, no matter how patient the travelers, the speed of light will not become merely another number to exceed. According to everything modern science currently understands, it is woven into the very structure that allows the universe to possess a coherent history. It is the rhythm by which distant galaxies communicate with us, the pace at which gravity reveals changes across space, the thread connecting every observer to every event. If one day a deeper theory replaces our present understanding, it will almost certainly explain why this remarkable limit exists rather than simply discard it. History suggests that successful theories rarely destroy what came before. They place it within a broader framework. Newton remains extraordinarily accurate for ordinary speeds. Relativity extends Newton. Quantum mechanics extends classical physics without erasing it. Future discoveries may extend relativity in ways we cannot yet foresee, but they will still need to account for every successful experiment performed over the past century. The universe has earned our confidence because it has been astonishingly consistent. There is a quiet comfort in that consistency. It reminds us that although human understanding evolves, nature does not change its answers to accommodate our expectations. Instead, it patiently waits for us to ask better questions. Perhaps that is the most remarkable lesson hidden inside the speed of light. At first glance, it appears to tell us what we cannot do. We cannot accelerate beyond it. We cannot send information faster than it. We cannot casually cross the galaxy within a single ordinary lifetime. Yet viewed another way, it tells us something far more meaningful. It reveals that the universe is not arbitrary. Its laws possess an elegance that stretches from the smallest particles to the largest cosmic structures. The same principles guiding photons across billions of light years also govern the ticking of clocks aboard satellites orbiting Earth. The same geometry shaping black holes also determines how a beam of light travels through empty space. Our own existence unfolds within that same framework. Every sunrise reaches us because light requires time. Every constellation is a glimpse into history. Every observation of a distant galaxy is an act of looking backward across cosmic time. Without the finite speed of light, astronomy itself would become something entirely different. Perhaps the greatest irony is that a limit often perceived as restrictive has become one of humanity's greatest sources of discovery. Because light travels at a finite speed, the universe preserves its own past. Because space-time possesses this remarkable geometry, distant history remains visible. Because information cannot arrive instantaneously, the night sky becomes a record of cosmic evolution. The boundary that prevents us from traveling as light does is the very same boundary that allows us to understand where we came from. And so we return to the quiet paradox with which we began. The speed of light is not simply the fastest speed in the universe. It may be one of the fundamental reasons the universe is understandable at all. We have learned why approaching it transforms time, distance, energy, and survival. We have seen how it shapes stars, galaxies, black holes, and the evolution of the cosmos. We have reached the edge of what present science can confidently describe. Beyond that edge, the future remains unwritten. Somewhere, perhaps centuries from now, another generation will build instruments that reveal what ours cannot. They will ask questions we have not yet imagined. They may discover that the deepest secret of the speed of light is not that it limits us, but that it points toward an even more profound understanding of reality still waiting beyond the horizon. And until that day arrives, the universe continues to send us its oldest messages, one quiet photon at a time.